Hello and welcome back to Organic Chemistry. Today we're going to be talking briefly about some properties of alkenes. So one thing that you need to know about alkenes is a little bit about nomenclature. So what I wanted to do is show you 3 examples of alkene nomenclature, and the book does a pretty good job of explaining this, so I won't go into too much detail. So here's a molecule that you should know how to name already. So if I was to go through and name this, I would start counting carbons here. Go 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the longest carbon chain. There is a substituent at the 4 position, which is ethyl. So this molecule, and you should know this by now, is 4-ethyl octane. Okay, so what happens if I were to put an alkene or a double bond in here? Well, the alkene has to be part of the parent chain, and you can see over here where the double bond was put, right, was not part of the parent chain. So over here the alkene has to be part of the parent chain, and the first carbon in the alkene has to have the lowest number possible. So in this case, I have to start here and say that this carbon is 1, 2, 3, and then I can either go this way or this way, and this way is longer, so I'm going to go to the left. 6 and 7. So this is a heptane, it's 7 carbons long. There's 1 substituent on it, so that is a propyl because it has 3 carbons. So this is 3 propyl, and then the alkene starts, the lowest number on the alkene is a 1. So I say that this is 1 hept, and then instead of heptane, which would be an alkane, it's an alkene. So instead I say heptene. So notice that E at the end. And the placement of the alkene goes before the name of the parent chain. Okay? So when I have an alkene that has a geometry, E or Z, I also have to include that. So if I look at this, I can start either at this end or at this end, and I'll include the alkene at the parent chain. If I start at this end, my alkene is going to start at 4. If I start at the other end, and we count, it'd be 1, 2, 3, 4, 5. So I have to start counting here because the alkene is going to have the lowest possible number. So if I start looking at substituents, I have a methyl at the 2 position. I have this guy, this V-shaped thing, at the 5 position, which is called isopropyl. And then I have an alkene at the 4 position. Okay, so if we look at this alkene, we talked about E versus Z in class. So the priority group is this guy, and then the isopropyl, because the isopropyl has 2 carbons attached to this carbon, and this carbon only has 1. Right? So the 2 priority groups, the isopropyl and this guy right here, are on the opposite ends. So this is an E alkene. So this is E, and then isopropyl comes first alphabetically, followed by methyl, and then the alkene is on the 4 position, so it's 4-nonene. And that's about as complicated as it's going to get. There could be some additional like chlorines or fluorines or bromines, some halogens in there as well. But this is how you name a molecule if it has an alkene in it. And the alkene always takes priority over anything else that we've talked about so far. Okay, so we're also going to talk about the stability of alkenes. So the way that we kind of determine stability of alkenes is by looking at something called heats of hydrogenation. So there's a reaction that we can do where we can take an alkene and we can add hydrogen gas to it and with some sort of catalyst. So this is a metal catalyst, this is platinum. And we'll talk about different ways of doing this and the mechanism of this when we get to chapter 9 of the book. So what happens is if you add hydrogen gas and a metal catalyst, you take the alkene and you form an alkane. So it just basically gets rid of the alkene. So it turns out that when I have a trans alkene, like this one, I end up getting butane as the product, and delta H for this reaction is negative 115 kilojoules per mole. Okay, so alternatively, I could take a cis alkene, so on the same side of the molecule, I can add the same reagents, hydrogen gas, platinum, and I get the same product in this case. And delta H for this reaction is negative 120 kilojoules per mole. So this reaction gives off more energy than the trans reaction. Finally, I can have a monosubstituted alkene, so an alkene that only has one substituent on it, where all other three things are hydrogen. I can do the same reaction, and delta H for this reaction is negative 126 kilojoules per mole. Okay, so you can see that going down this list from trans to cis to mono-substituted alkenes, we're giving off more energy. So what does that mean in terms of stability of alkenes? Well, we can chart this. So here's our mono-substituted alkene. And we said that when we heat, or when we hydrogenate, we use that hydrogen gas and platinum, we end up with this product, butane. And it gives off 127 kilojoules per mole. Okay, alternatively, when I have a cis alkene, it gives off 120 kilojoules per mole. And when I have a trans alkene, it gives off 115 kilojoules per mole. Okay, so in the end, what this means is because we're giving off more energy for the monosubstituted alkene, the monosubstituted alkene is going to be less stable or higher in energy than the cis alkene, which is higher in energy or less stable than the trans alkene. So the take-home message for this is, first, that trans is more stable than cis, and second, that di-substituted alkenes that have two substituents on it, are more stable than monosubstituted. Okay, so why is this the case? Well, we can look at the different molecules and kind of figure this out. So let's first think about cis versus trans relationships. So we said that cis is less stable than trans. So if we look at a trans alkene, so this is that butene again. You see here, I can show you kind of the steric space that these two methyls are going to take up. And you can see that these two methyls are on opposite sides of the alkene, and they're nowhere near each other. They're kind of separate from each other. Alternatively, if you look at the cis alkene, these two methyls are right up next to each other. They're on the same side of the alkene. If I kind of show you where the space is on these, you can see that they're kind of bumping into each other. So this desire for two atoms to not take up the same space is the same as what we've seen before, and this is called sterics. So what sterics tells us is that the cis alkene is less stable than a trans alkene. So the reason that monosubstituted is less stable than disubstituted is a little bit trickier. So if you'll remember back when we talked about carbocations that are more substituted are more stable. So tertiary is more stable than secondary, which is more stable than primary. And the reason for that was that these other carbon-hydrogen bonds next door can donate electrons into the p orbitals of the carbocation. So the same thing is true for an alkene. These orbitals that are between the carbon and the hydrogen, these sigma orbitals, this is sigma bonding orbital, can donate electrons into the pi orbital of the alkene, which is a stabilizing factor. So what ends up happening is that hyperconjugation will increase the stability of substituted alkenes. So the more substituted your alkene is, the more stable it is. Okay, so let's just look at an order of stability for alkenes. So the more substituted, the more stable. So this is a tetrasubstituted alkene, which is the most stable type of alkene, followed by a trisubstituted. And then we have three different possibilities for disubstituted alkenes. So these are all disubstituted. And it turns out that there is an order of stability for these. So we know that trans is more stable than cis, and that's because of sterics. And it turns out that this type of alkene, where both of the R groups are on the same carbon, these 1,1 disubstituted alkenes, where they're both on the same carbon, is actually more stable than trans and more stable than cis. Okay, and then finally, the least stable type of alkene is a monosubstituted alkene. So that is alkene stability and alkene nomenclature, and I will see you guys in class very soon.